Right, hello everyone. Thanks very much for inviting me here today to all of the Data Science Festival team. I hope you can hear me okay. It's a pleasure to be back here at this fantastic festival, presenting this year on one of my favorite subjects, which is generative deep learning. As Ian said, it's a topic that I've written a book about recently, all about how to build these kind of models from scratch. So kind of going from first principles right up to what state of the art looks like. It's a book that covers a number of different areas of creativity, so not just images, which is typically where generative deep learning is applied, but also in the fields of text and also music. And then lastly, I think one of the most interesting areas, which is the application of generative modeling to reinforcement learning, which is another one of the key pillars of machine learning, as I'm sure you know. And this talk really is kind of bringing these ideas together to ask, I think, one of the crucial questions that we need to answer, which is, how do we build machines that are truly intelligent? And if you can think deep and hard about this, you quickly come to the conclusion that generative modeling must play a part in this quest. It's not enough to just focus on supervised learning or indeed just reinforcement learning. But there's this idea that we need to build our machines to be generative, and we need to build them to ultimately create things. And it's that art of creation that will, I think, lead one day to intelligence. So as Ian mentioned, this talk covers a wide variety of topics. We'll go from scratch, so there's no prerequisites needed in terms of knowledge of what generative modeling is. So we'll go into detail, first of all, on how you get started with these kind of models. As mentioned, I'm a Python programmer myself, so the book is it has tons of examples of how to build these models from scratch, and I've worked code examples and all of the things that you'd expect really from a book that goes from first principles. And I think one of the key models that I certainly started with when I was learning about generative modeling is the Variational Autoencoder, and that's the subject of the second section. The Variational Autoencoder is really one of those kind of models which is beautifully simple to understand, but you can do very impressive things quite quickly with, which is a perfect kind of introduction to how to get started with generative modeling. We're then going to move on to the reinforcement learning side of things with one of my favorite papers. It's a paper called World Models, written by David Ha a couple of years ago now, but it's still highly relevant today because it introduced, I think, for pretty much the first time, the concept of how generative modeling and reinforcement learning can be linked. And then in the last section, we'll just expand a little bit on that idea and just run with some ideas about how that might relate to AGI. So let's start then with an introduction to generative deep learning. So generative deep learning is a dictionary definition, you might say, is it's a type of model that can create new observations. So with typical machine learning, what you're looking to do is predict something about an image that's given to you. So whether that's, for example, a face that you're given and you want to know if it's smiling or unhappy or angry, that's the typical discriminative model. But a generative model actually looks to solve what I think is a harder problem, which is how do you, given a set of images, try to produce a new image that looks as if it was drawn from the same set. So what you can see here in the bottom right is a style GAN. GAN is a Generative Adversarial Network that has been trained to try to replicate the Celeb-A training set of data. And there's a couple of things you can see here straight away. First of all, it does so in what's called a latent space. And it's a key idea of generative modeling that we often embed the observations, or we try to embed the observations into a latent space, a hidden low dimensionality space that we can manipulate and we can perform arithmetic within in order to manipulate the pixel space of the image. So we're going to be seeing how to do exactly that with a variational autoencoder. And it's really impressive when you look back, even 4 or 5 years ago at what was achievable through to the present day. There's actually a fascinating article you should check out in the New York Times that was released yesterday, actually, showing exactly this progression and also some of the core ideas that we'll be talking about in this talk. So I'd highly recommend that you check that out. But you can see here that the progress is astonishing and is set to continue actually into the years going ahead. And I think it's getting to the point now as well where, you know, we look at these images and they are so indistinguishable from the ground truth that we start asking ourselves bigger questions like, okay, we've kind of solved this problem. Now, what do we do with it? Can we move into video? Can we start using these images to actually train things that can spot adversarial examples and therefore avoid the whole dilemma with fake news and trying to spot things that are not true before they get out onto the internet and convince a lot of people. So there's a lot of big sort of philosophical questions that need to be answered. But certainly, if you look backwards over the last 6 years, what we can say is that the progress has been astonishing. That's got us to this point. And I want to start with a toy example. That's always the best place to start, I find, is to reduce ideas to as small as possible so that you can really get a grasp of what they're doing. And I want to ask you a question, which is, if you were to try to produce a new point in this space that looks as if it's been drawn from the same distribution as these points, where would you pick? And instinctively, you would probably try to pick a point that is nearby an existing point, but not certainly on top of, because then you're not really achieving too much. So you would probably pick a point maybe in the top right of the quadrant, but probably not so likely to pick a point, for example, in the bottom left of the quadrant. What you also might like to do in your head is think to yourself, well, I'm just going to draw a box around all of the points that I've seen so far, and I'm going to pick a point at random within this box. And that is actually an example of a generative model, because you have a distribution over which you can sample, namely a uniform distribution over the box with 0 probability of picking a point outside. And it certainly represents these set of points. You've used the points to build this distribution. So it is a learnt model in some regards. You've used the edge points of the data in order to draw this box. So what we have here is our very first example of a parameterized generative model. The parameters being the edges of the rectangle and it's being learnt from the data. Now, there's some of these points that were in the box that were actually not created by the true data generating distribution. If we layer on top what that looks like, we can see that actually these points have been generated by choosing uniformly over the world map. And so what we've done with this rectangle is tried to simplify the true data generating distribution. We've tried to build a model of it, and we know it's not perfect, but it was a pretty good first attempt. And you can see that this starts to create some things in the sample space that are false, such as a point in the middle of the Atlantic, for example, wouldn't have ever been generated from the true data generating distribution, but would have been generated by our model. And likewise, there are some points, such as in Alaska in the top left there, which would never have been generated by our model because they were outside the box. But in reality, they could have been generated by the true data generating distribution. And so the point I'm trying to make here is that the model and the true data generating distribution need to be as similar as possible in order for us to be convinced of the accuracy of this model. And the important thing to realize here is that we don't know P data. P data is hidden to us. It's a bit like saying, could you write down the distribution of all possible images of faces? Well, obviously that's impossible, and nobody knows what that looks like. But we can certainly test if two distributions are similar, and that's effectively what we're going to be doing with our first example of a model, a variational autoencoder. We're going to be testing to see how close can this generative model get to what the actual data looks like from the training set. And so that's kind of like an intuitive understanding of what we're trying to do with generative modeling. I think it makes sense now to talk a little bit about why this is difficult, because in 2D, this is obviously very simple, but when you start looking at images of faces, the whole dimensionality of the space is much larger and therefore much more difficult to find a true example. You can see here, for example, if we take a 1000 by 24 pixel by 1024 pixel image of a face, each of these pixels has 3 color dimensions as well. So you multiply all of these together to get the dimensionality of the space that we're trying to operate in. Every single one of these is possible as an image, every single value of a pixel in every single position. And therefore, we have to ask ourselves, how difficult is it to generate a face that looks realistic? And the answer is extremely difficult. If we were picking at random, you would just get white noise all over the place. But even if we build a model that seems to be doing something intelligent, there's other problems, such as how do you make sure that a green pixel on the right-hand side of this image is the same shade as the green pixel on the left-hand side of the image? If they change, then we as humans instinctively know that there's something a bit amiss perhaps about this generated image, because in reality, you wouldn't have a background that switches for no reason. Or indeed the jumper that he's wearing, for example, that wouldn't just suddenly change color. So there's lots of different problems that we have to tackle when we're discussing generative deep learning that can be summarized neatly into these two. The second one we've already discussed there, that well-generated observations are extremely sparse. And the first one relates to the point that I was just making about the background, making sure that it's consistent across pixels. And there's this conditional dependence between these pixels that is highly important to capture, because if we don't, then the game's up, really. We know exactly that we're looking at a generated image. Deep learning helps solve both of these problems. That's why it's been so powerful. It's a technique that deals extremely well with high complex conditional dependencies, especially in images where two pixels that are over opposite sides of the image can still be linked within the model through techniques, for example, such as convolutions, which tries to effectively layer over a convolutional matrix over the image and try to capture in increasingly deep layers what is in each part of the image. So even though you still have pixel space going into the neural network, within each layer subsequently is able to learn something slightly more abstract about that image. So for example, whether it's an eye or whether it's a jumper part of the image. And through learning the parameters and through showing it many examples of what typical faces look like, it can do this extremely well. And so we're going to see our first example of a generative deep learning model now in a variational autoencoder. And again, we're going to start with a toy example to get used to what this type of model does. So I want you to think to yourself, if you were to be asked to generate a new image that belongs to this set, how would you do that? And I think we'd all be able to understand intuitively that there are two dimensions along which these images exist. There's the height dimension, and there's also the width, or indeed the depth. So because we instinctively understand that there's two dimensions to this image, we know that we can choose two values of those dimensions and come up with a legitimate looking cylinder, even though we haven't seen all possible cylinders in that possible space. And so you can visualize that in this way. We've encoded as humans these cylinders into a two-dimensional latent space of height and width. And then as humans, we also have the instinctive ability to decode any one of these points in the space back into pixel space, even though we've never seen them before. And that's what we'd like our generative model to do. We'd like it to be able to learn what a good latent space would look like for this set of images. And then once it's learned that, to also learn how to decode any point in that space. And it's quite a beautiful idea, really, when you think about it, is that we're capturing something that's very high dimensional in a lower dimensional space in order that we can intuitively understand it better. It's the idea that ultimately all of this complexity comes out of something that's very simple, in this case, just two numbers. And so we're going to do exactly that with a neural network. So if we just sort of speak generally, we don't use kind of neural network terms or anything, we just talk about what we want this thing to do. Well, we want one part of the network to encode all of our training set images into the latent space, and we call that the encoder. And then we want another neural network that takes any point in the latent space, just two numbers, and decodes it back into a pixel space that we can look at and say, yeah, that looks like a cylinder, or that doesn't look like a cylinder. And so just to speak briefly about what these actually are, An encoder is just a neural network that has many layers of nodes that are connected by weighted edges. And a neural network, if you haven't come across them before, is just simply a way of training this that uses backpropagation. So it takes the error out of the back of the network and tries to work out how much of that error it should assign to every single weight in the network. And it uses differentiation techniques to be able to work those things out. And so the core idea that we need to understand is how to train this thing, right? Because all we've got is a set of images. We don't have any labeled data. We've just got images of cylinders. And the key is to really realize that we can join these two things together in the middle and train it as just one network. We don't need to train them independently. We can just train it as one. And we call that an autoencoder. So the way this works is that we simply pass every single image in the training set through the encoder. We get a length 2 vector that represents what that looks like in the latent space. And we push that through the decoder to get back to pixel space. And then we just say, well, how close are these two pixel space images? And we use the root mean squared error simply on the pixel values in order to determine how similar they are. So where the two images are identical, that loss would be 0. They would be perfectly aligned. And where they are slightly out, or some of the pixels were a different color from other pixels, then we would start to see a loss. And that's how the neural network knows that it's not doing as well as it could be. And so this, again, the first time you see this, this kind of appears very strange. Why would we want to basically produce something on the right-hand side that is identical to the left-hand side? And the answer is that the latent space is what we care about. We don't care about the output of this neural network. We just care about how it's represented the input in the latent space, because that's the sample space that we're going to be choosing our new observations from in order to generate potentially new looking cylinders. So I want to switch now to a slightly different example, which is the MNIST data set. And it's the same idea. We're passing in handwritten digits now, this time into the left-hand side, and we're getting out potentially new looking handwritten digits from the right-hand side once we pick a point in the latent space. And you can see in the bottom right here, this is how an autoencoder represents the input data in the latent space. And you can see I've colored the points here by the actual digit that they are representing. And the autoencoder has found a way to group together similar digits. So all of the ones are grouped together, all of the twos are generally close together. And that's not because we've told it to do so. That's just because it's useful for them to be close together, because then it knows, the decoder knows how to decode them back into pixel space. If, for example, all of the twos were like spread out all over the place, how would it know when it picks a point in the space whether it should decode it to a 2 or something like a different looking digit? So instinctively, it makes sense that these things all clump together. But there are a few problems with sampling from this space if we want to generate new points. First of all, it's really poorly defined, right? So how do we know that we can't choose the point a million in this space? What's to stop us? Well, nothing really. It's just the space of real numbers in 2 dimensions. So even though the model has chosen to put them between about -10 and 30 and -30 and 5 on the other axis, that's just kind of completely arbitrary. There's no reason why we can't choose a point outside that, and therefore we're not guaranteed to get anything interesting if we do choose a point that's miles away from the training data. And secondly, the problem is that local continuity is in no way guaranteed. So that it can leave huge holes in this space and not fill them with any training data. And it doesn't have to, because it's kind of got an infinite amount of space to work with. So it just chooses to put them wherever it wants, based on essentially the initial conditions of the neural network. So there's a kind of one trick that helps solve both of these problems, and that's where the variational autoencoder comes from. It tries to solve these two problems. And the trick is that instead of simply encoding every point in the training set into a single point in the latent space, so like this 7 might get decoded to, it might get encoded to like 1, 1. Instead of doing that, what we do is we encode into a normal distribution. So what does that mean? What that means is that the number 7 on the left-hand side here gets encoded to a mean and a standard deviation. So instead of a single point, it's now a fuzzy area in the latent space that basically means that there's some randomness about where this 7 might be. And it seems again strange to be imprecise about where this 7 could land. But what this does is it helps the decoder, because it ensures that the local area around this mean, it also has a chance of decoding to what looks like a 7 on the right hand side. And so like the kind of intuitive way about thinking about this is if every single time I encode this 7, I just encode it to a single point, there's no incentive for the decoder to decode something just to the right of that point to a similar value. All it has to do is make sure that it gets that 7 right. But if suddenly there's a fuzziness to where this 7 might land, then the decoder needs to make sure that it's aware of this when it's decoding, and make the local continuity a lot stronger. That's the best way of kind of understanding it intuitively. And the second reason that this is very important is because what we can do is we can add an extra term to the loss to ensure that the distribution that it's encoding into looks a lot like a standard normal. Standard normal being simply a normal distribution with mean 0 and standard deviation of 1. And in 2 dimensions, it's simply a normal distribution centered around the origin with standard deviation of 1 in every direction. And again, why is this important? Well, this kind of solves 2 things. Firstly, it forces everything towards the origin. So you can imagine this as kind of like an attractive force that ensures that the things that it's encoding get as close as possible to the origin, but not so close that it then can't make the distinguishing, be able to distinguish between different kinds of digits. And when you add the way that we enforce this condition, this standard normalization, is through something called the Kullback-Leibler divergence, or KL divergence, which simply tests what's the difference, what's the distance between the standard normal distribution and the mean and standard deviation of all of the training set data. And if we add that in, what we're essentially telling it is make sure that you don't make these normal distributions too dissimilar from standard normals, but it needs to have some leeway to change away from that so that it can actually make the it can distinguish between all of these different features so that the decoder can do its job properly. So they're the 2 real changes that you need to make. You just need to make sure that it encodes into a fuzzy area, and that we add an extra term to the loss function, which encourages it to do this in a way that makes it look like a lot like a standard normal. The best way to view this is just by looking at a picture of the latent space in the new world of the variational autoencoder. And you can see here on the left exactly what we were talking about. This looks a lot like, if you ignore the colors, a standard normal distribution in 2D. And that's because it's been encouraged to make it look like this. And you can also see that on the right-hand side here, this is when we just transform from Z space to P space. And you can see here that this is a very full looking P space. There's not many holes now. We've kind of filled the space completely, and that's because it's been made to look as much as possible as if we're drawing from a standard normal. The really nice side effect of this is that it means that we can simply sample from a standard normal distribution in order to choose a new point in this space. So whereas before we had like an infinite space to choose from, now we can simply just draw a point from a standard normal distribution and then see what that decodes as. And we get hopefully something that looks like an interesting digit, that it might be sort of a cross between 2 different digits if it's between 2 different areas, but hopefully we get something that looks a lot more realistic. So you can imagine here, if I'm moving around this latent space on the left-hand side and decoding every single one of these 2-dimensional points, you get something that looks like the right-hand side, where any one of these could legitimately be something that you might draw from, draw as a handwritten digit. And you can see there's this nice smoothness between the transitions. It's not jumping from something that's just completely, say, black to like, oh, and there's a digit, and then it goes into something that looks just random noise again. It's everything in here looks legitimate. It's a good example of a generative model. And so that's like a crash course really into what a variational autoencoder is trying to do. And although it's a very simple explanation of what a generative model is, it's, for example, much simpler than generative adversarial networks, which are somewhat more difficult to train. It still gives a good idea about what their power and why it's important to care about things like the latent space and continuity and all of the amazing things that that allows you to do. So I want to talk now briefly about the concept of a world model. And this is where we start to ask the question, well, can we incorporate these generative models in order to make reinforcement learning algorithms stronger and to make the agents able to learn better? So a very quick introduction to reinforcement learning. This is where we have an agent and we have an environment that agent lives in. And at each time step, the agent gives the environment some action that it wants to take. So in the case here, it might be driving left or driving right or accelerating. And then the environment gives back two things. It gives the agent back a reward. So did it do something well or did it not do something well? Maybe like 1 if it does it well and 0 if not. And then the next state. So obviously the agent needs to know what happened. So in this example, it would give it back the pixel image of the next, where the track is in relation to the car. So you can see here on the right, this is an agent that's been trained to drive somewhat well around a track, not perfectly. I think you'd probably fail your test if you were driving like this around your track. But yeah, this is a good example of how, for example, the reward here might be that you hit the next section of track. That would give you a reward of 1. If you drive off the track, you get a reward of -1. And so what they did in the world models paper was ask the question, how can we train an agent to learn how to do this, i.e. drive around the track? But how can we do this without it ever having tried to do this in the past? So what they did was, this is a very similar diagram to the one we've just seen, with the environment being at the top and the agent is the rest of the picture. And you can see, let's just follow it from the top. So the environment gives the agent a state. But now what happens is that the state gets passed through a variational autoencoder in order to generate this Z value. And the Z value is nothing more than the two-dimensional latent space representation that we've just been seeing in the previous example of the cylinders and also of the digits. In their case, their Z was actually 32 dimensions, which sounds still really high, but actually in comparison to the many thousands of dimensions in the original pixel image, it's a compression. Then what they did was they gave this Z, which is just a vector, to a world model. And a world model is just a recurrent neural network that tries to predict how this Z is going to evolve in the future. So you can think of it a little bit like it's like a prediction engine for Z. So if like Z is our latent space, our vector in our latent space, what's the next Z going to look like given I take a certain action? That's what the world model is trying to predict. And if you know a bit about recurrent neural networks, you'll know that there's a hidden state called H that it tries to maintain to understand what's going on. And that's also just a vector. And then the controller on the right-hand side is trained, actually, it's just a deep neural network. So multi-layer kind of standard kind of, multi-layer neural network. And it's not trained through backpropagation because there's no labels. We don't know what a good action is and what a bad action is. But the controller is there to simply say what action it thinks the agent should take in the next time step. And it does that, it learns that not through, as I say, not through supervised learning, not through backpropagation, but using an evolutionary algorithm to test lots of different agents in the environment at once, see which one gets the best rewards, and then update its weight parameters based on which of the agents got the best score in the environment. So over time, this controller becomes stronger and it starts to predict the actions that eventually score at higher points in the environment. And so what's the point of the variational autoencoder here? Why is that an important thing? Well, if we look at a trained example of this, it's important to realize that the variational autoencoder is actually just trained on data that's random movements in the environment. So at this point, the agent isn't trying to kind of drive around the track quickly. It's just taking random movements and then essentially just trying to recreate those images in its variational autoencoder. So it's trying to make this latent space as accurate a representation of the environment as possible. And you can see here in this little demo that it does this pretty well. So given a pixel space image from the environment on the left, if you pass it all the way through the variational autoencoder and see what comes out, you get something that does look exactly like the real life image. So whatever is being encoded into the latent space is a good representation of the environment. And again, it's important to recognize that this is trained entirely independently. So the training data for this is just, but you basically say to the car, just drive randomly around this environment for a bit and just pick up some training data, like just go and collect some. So every single time step, it sort of captures an image, stores it in its memory, builds up a huge bank of training data of stuff that happens in the environment, and then tries to build a variational autoencoder on it. So there's no rewards, there's no reinforcement learning going on at this point. It's just train a variational autoencoder based on data that you've picked up from the environment. Now, the important thing about this VAE is that it can obviously generate new observations. And we can show this by, if we just fiddle around here with some of the Z values, so these are individual values of the 32-dimensional vector, you can see that the space is continuous, exactly like we'd expect. So it's learned that there are things in this environment that could happen that it maybe has never come across before, but actually within the latent space, everything is possible. And therefore, just like the cylinder example that we saw right at the beginning, it's trying to imagine where the in-between points are within this pixel space. And there's obviously some of these tracks that it's never come across, but as long as it can imagine that it could come across them, that's what's important. And we can see why it's important, because what happens is then the world model is able to learn from the Zs that it's come across before, how those Z values evolve. And that applies not only to things that it's come across before in the training set, but of course also to things that it's never seen before in the latent space. And therefore, this is what makes the whole thing so powerful, is in a nutshell, the agent is able to imagine things that it hasn't seen and reason about how those things evolve over time using the world model. And the next big step of the paper was to realize that this world model is effectively an environment in its own right, because it's just trying to imagine how this Z value evolves over time, given an action. And that's exactly what an environment does. It's just that the environment works in a pixel space and the world model is working within the latent Z space. So an environment obviously is based on rules and physics, and like it's just the environment that you get given to you. But the world model is trained. It's something that learns over time how Z evolves based on the actions that it's taking. And therefore, this was the key step, was to realize that the entire environment can be replaced with the trained world model. And that's what they called the dream environment in their paper. And just to go slowly through this, there are now 2 copies of the world model. There's one at the top there, which is acting as the environment. So that's been trained as the dream environment based on random movements that the agent has taken. You can imagine that as like in its infant years, just as it's crawling about as a baby. And then there's the second world model at the bottom, which is the world model that it's training now that it's been given a proper task to do. So go and drive fast around this track. But of course, the amazing thing is that it can learn how to do this without ever having seen the real environment. It's doing this entirely based off of its own world model understanding about the physics of how this environment operates in latent space. So that's a big idea to get your head around. But the important thing to recognize is it means that agents can learn how to do things without ever having tried them in the real environment at all. And you can see actually in the next slide, this is this is a image here of the agent training itself in its own dream. So it's a bit laggy actually. That's unfortunate, but I'll play it again in a minute. Oh, there we go, that's a bit better. So you can see now, this is the agent imagining itself driving around the track and the things that it might come up against in the future, and giving itself internal rewards because it learns how to model those as well. And it's so encouraging itself not to drive off the track, for example, because it knows that that typically is a bad thing to do, but also imagining what future track might look like in coming up, that it's coming up to in a corner, for example, and how it has to deal with that. And so the controller and the world model here are being trained to recognize how to do this, so that ultimately you get an agent that is in fact just as good as you would do if you trained it in the original environment. And we can see that here. This is the results from the paper. So the full world model at the bottom there actually scored 906, which is the highest score that anyone had achieved in this environment at the time. And it beats even models that were trained using the environment itself. So you have to remember, this is the full world model has been, the variational autoencoder obviously has been trained using the environment, but once it's got that internal understanding of the physics of how things operate, it doesn't need the environment anymore because it has the latent space, which is a perfect representation as far as it's concerned of what happens in reality. And it maps across all of the actions that it's taking in its latent space, are mapping perfectly back across to the pixel space and the real environment. And so I just want to finish up if we have time. I haven't got the clock. Let me just find out the time. Yeah, okay, I think we've got 5 minutes. So I just want to briefly mention a few things about artificial general intelligence, because I think this idea is critical. So let me explain why. If you kind of think about AGI, not from things that you've read or like things that things you imagine AGI should be, but just think like, what do we expect them to do when we place them in an environment? What do we expect agents to do? An agent with artificial general intelligence. And you might start thinking along the lines of, well, they've got to learn through reinforcement learning because that's an important thing. And we give it rewards about something and it learns the correct actions to take. Or you might start thinking along the lines of supervised learning, that it's got to somehow pick up a huge amount of labeled data and then make predictions that are really accurate, and we'll be really impressed by that. But actually, when you think about it, all of these things that we talk about when we talk about reinforcement learning and supervised learning are a priori constructs that we have to give the agent. The concept of a reward doesn't exist in nature. Nothing is labeled. There is no such thing really as a prediction. We just do stuff. It's not like we say, this thing that I'm now making is a prediction. It's just an action that another thing that we do in the environment. And even actions aren't particularly well defined. A baby doesn't come ready-made with the actions that it knows it's able to take. It's able to move limbs in any one of number of directions. It can make noises. How does it know how to manipulate its own being, if you like, in order to infect the environment in the way that it wants to? The actions are particularly poorly defined. So what does this mean? Well, what I think it means is that generative modeling is the only thing that a new agent in an environment can do. Realistically, there is only one thing it can model, and that is its own ability to predict what happens into the future. And by predict, I mean generatively model the future and then see if it did particularly well at modeling that future. And the important thing to remember here is that, of course, includes the agent itself. There is no such thing as just modeling the environment generatively from a kind of like standoff point of view, from a distance. You are the environment. So anything that you take, even moving your head, can completely change the input data that you're receiving. It completely change it. So when we're talking about generative modeling, I think we also need to realize that we're not only modeling the environment, but we're modeling what we do in the environment. And it's quite a sort of complex thing to get your head around, because then you start thinking, well, where's there seems to be a feedback loop here. Like, who's making the decisions? Are we moving our head because we want to move our head, or are we moving our head because it helps us generate better training data for the future? And there's obviously a lot of gaps in our knowledge here when it comes to how learning takes place in infancy, not just in humans, obviously, but in all intelligent life forms. And so, people have started talking about this, and it's not just an idea that's coming from machine learning, it's an idea that's coming from neuroscience as well. There's a number of papers recently that have talked about a generative adversarial brain, a number of papers that talk about generative modeling a little bit more generally and where this might sit within the brain, and also about how the different connections that we see in terms of neurons can come to realize what might be described as a generative model. Now, I think, at this stage, it's important, I think, especially for a talk like this, is that we don't try to go into too much detail on any one of these particular ideas, but we just talk generally and think what this might mean for where we focus our efforts going forward in terms of generative modeling and AGI. And I think, from my thoughts, one of the most exciting things, I think, is the concept of an auto-generated reward. Most reinforcement learning still is based on rewards that the environment gives the agent. And I think that's wrong. I think if we're going to build something that's truly intelligent, the reward needs to be self-generated. The agent needs to give itself a reward based off of some perhaps higher level objective that it's trying to achieve. But ultimately, the short-term rewards that it's being given are flexible and can adapt itself to its current situation. And I think that applies for everything: labels, actions, everything is up for grabs. How it defines an action, how it defines a label, how it defines a reward are all things that the agent needs to learn tabula rasa, if you like, from scratch, without any prior input from the environment to tell it what to do. And if you look at like, try to find examples of this, I think this is as good as you can find, to be honest. So this is a video of an agent in an environment, we might say, and there's no task. The environment hasn't told it what to do. There's no incentive here for it to do anything. It's just, I think, what we're seeing here is the ability of the baby to generate a future for itself and to imagine what might happen if it takes certain actions in the environment, and to give itself such an incredibly positive reward for seeing the environment replicate what it believes should happen. And I think that's the key, really, is to understand how do we put this ability into machines. It's not just the ability to explore, but it's the ability to know what to explore and to be truly amazed when your own latent space of what should happen matches accurately the real world. And so I think auto reward functions and auto-generated functions are the way to do this. I just want to finish up with a quick quote that one of my favorites from Richard Feynman is, "What I cannot create, I do not understand." And it's true of all learning, I think, when it comes to data science or anything that you're learning about, is to teach it, to write about it, to write blogs about it, to produce something on your own that helps further your understanding. And we can adapt this, I think, as well, to what AI cannot create. AI doesn't understand. It's going to be really important going forward that generative modeling is a core component of what we consider AGI to be, not just from toy examples and kind of producing things that look similar to what a human could produce, but I think it's at the very fundamental of what we mean to be intelligent. So thank you very much for your time, and I'm really happy to take any questions that you might have about anything you've heard today. So thank you very much.
Okay, David, thank you. That was a fascinating talk. Loved it. Really, really good. You even jumped off in the deep end with the philosophy at the end. So thanks for that. I'm going to snake in with a quick question that I've got before we go to the Q&A from the guys. Steering off the fascinating AGI stuff. With the autoencoder, would you say that when you, for that MNIST example, that you've got all of the cases of the real handwritten digits, and then you train a network that then learns where it thinks the boundary between a 3 and an 8 are, for example. And then what we would get in the trained network, if we were to put exactly the same digit in, we would get the same out. So what the variational encoder is doing in some way is allowing variation in that input to give it different examples to use for training, but in a way that is consistent with the boundaries that it's learned overall. Would that be a fair estimation of it?
Absolutely, yeah. When learning variational encoders, there's kind of two ways you can approach it. There's either from the very statistical side, and it's very mathematics heavy, and it's very kind of, there's a like a pure way of evaluating that a variational autoencoder is the right thing to do. But then there's also the kind of technical, practical side, which is what I've tried to give here, which is more about what's the problem? Well, the problem is that it's trying to encode everything to a single point. And that's an issue because it's like, it's got so little incentive to make sure that there's local continuity. So like you said, by making this fuzziness around every single encoding, you manage to achieve what you want, which is a much tighter compacted space. And ultimately this beautiful property of moving from A to B gives you a completely continuous flow of true looking images along that line, so that you don't ever just get this massive kind of like cliff edge between them and where it all goes, you know, rubbish for a little bit.
Well, no, it's just really interesting that, because that's kind of put it in my mind that it's come out of supplementing data, which we often have to do to make the networks work, from supplementing that data to actually the method of supplementing in itself becomes the new method. That's really, really interesting. So on to the real questions. Alexandra Crasium asked, how did you generate the 2D image of the digit clusters? Just a fairly simple one to start.
Yeah, so that's all. I'm a Python coder. I code a little bit in R, but I'd always go for Python for stuff like deep learning. And that was coded just using some kind of matplotlib libraries.
Was it like you projected through the various dimensions? I think it's a TSNE or something, like where it works out the best separation given loads of dimensions, just at a guess. So Chris Schoen, the autoencoder question, do the data points on the edges of the standardized box have more distinct features, making them further from data points of the other classes? So this is to do with, I guess, the overall loss function and how you make sure that you're keeping a loss, you know, an overall loss consummate with what you want.
Yeah, so I mean, the autoencoder, the variational autoencoder, I should say, is always trying to make sure everything's treated equally and fairly. So there's no notion of like some data points are more important than others. It's trying to make sure that whatever it's doing, it's applying equally across all data points. But that probably makes it more important actually that you have balanced classes when you're training all of these things. And when I say balanced classes, I don't mean in the sense that you need labeled data, but I mean like if you had a data set which is full of 7s and a few 3s, it's obviously going to do much better at the latent space around the 7s than it is the latent space around the 3s. So that's true of all machine learning.
Make it similarly more inclined to predict 7s as per normal, you know.
Yeah, it would make it more inclined to generate 7s. Yeah, definitely. That's right. Yeah.
I see. Thank you. Okay, one from Jayant Gupta. Would there be an interest to use dependence between weight distributions instead of independent centered normal distribution for generating
Yeah, thanks for the question. That's a good question. So I think there's many different kinds of generated distributions you can use. The normal distribution is just one of them. The key is that it's got the property that you can A, sample from it, and B, it's a nice distribution that you can work with because you can use this KL divergence. And there's actually a closed form for the distance between a distribution and the standard normal. So you don't want anything where you're having to do like kind of estimate the integrals and all this sort of thing, because it slows the algorithm down. You want a nice closed form solution for the KL divergence, which is what the standard normal gives you. So I'm aware of some other distributions that people use instead of the standard normal, but I think that's the go-to that most people would use for variational autoencoders.
Lovely. Okay, another one from Elizabeth Hull. If the world model contains the agent, would this have to be a lower dimensional representation of the agent due to memory limits? Could this also be done via latent space representation?
Yeah, thanks for the question. That's great. So yes, I mean, I think one of the most interesting things is that exactly like you say, the world model has to include a lower dimensional representation of how its actions are affecting the environment as well. And it kind of, you kind of start thinking, well, does that mean that I'm kind of like, the way I imagine myself operating in the environment is therefore a simplification of how I am or how I could be, which again sort of
world.
Moves into philosophy. But I so to the point on like,
I'll get ready for the next few questions. But no, it's a really interesting one, that, because it's of course like, to what degree are our conscious ruminations lower dimensional representations as well. It's yeah, and where do the two kind of tie into each other? I'm going to try and see if we've got any more now. Let's get, before we go to philosophical, crikey, we've got an awful lot. I think you're going to have some answering to do on Slack afterwards here, David. Thomas Oliver, would a good self-generated reward be a reduction in the entropy of the incoming data? So the agent would try and minimize how much extra information it gained at each step while retaining a high fidelity record of the original. So he then says this could include a choice of actions like moving the camera around to get 3D information, or that kind of thing, to keep track of high entropy sources, as the question is worded.
Yeah, that's a great question again. Entropy is key with reinforcement learning. In fact, it's a term in PPO, which is the proximal policy optimization, which is a different kind of reinforcement learning algorithm. The idea with reinforcement learning, the core to all of the field really, is that you have to balance exploitation and exploration. So where, for example, an agent is simply exploiting what it already knows, you end up with a very short-sighted, probably suboptimal agent that thinks that it's doing brilliantly, but that's only because the data it's generating is very simplistic and not a representation of the truth. If you have too much exploration, you have the opposite problem, or entropy is the same, essentially the same thing as exploration. So you have to always balance these two, and it's not an easy balancing act to
Fascinating
make.
to think of all that in terms of the baby example at the end of the video.
Yeah.
It really is. It was such a good little analogy that I really enjoyed it.
Yeah.
Jamal Sondi, hi David, thanks for the superb talk. I don't have a mathematical background, but your book perhaps prematurely. Could you advise what mathematical prerequisites are needed to be able to build these models?
Yeah, it's a great question. So in terms of to build them, you need no mathematical background, because most of them are coding examples, completely. However, I wouldn't recommend you just sort of are satisfied by that, and you're right to start questioning what the mathematics are that you need to understand the models themselves. So, I mean, matrix algebra is a key to any deep learning, because effectively that's what it's doing. It's multiplying lots of big matrices together. So to understand how a tensor flows from input, at input, it's a two-dimensional image with another dimension for the pixel space. So you've got a 3D tensor there with another dimension for the number of images that you're putting in, all the way through to a latent space, which is a much smaller compressed version. You've obviously still got the batch size in there, but you also, it's just a 1D vector now, I should say. So to understand how that tensor flows through, matrix algebra is your friend.
Got you. Okay, so we're getting towards the end. I'm going to drift slightly towards the philosophical end. Now, Jeremy Helm asked, you mentioned self-generated rewards. How do we give direction to these? Now, I'd be thinking something like in the baby example, it's if you fall and land on your butt, then that's the world telling you made a bad call. But is there more to it than that, perhaps?
Yeah, I think so. I think this is the key question, right? I mean, this is what nobody really knows, is that an auto-generated reward by definition has to have something driving it. And I think what's driving it is that agents that are able to generatively model their environment more accurately naturally have this balance between inquisitivity, I think that's a word, and exploitation. And they just tune it just to the right amount so that they can effectively do things in the environment that are interesting. And I think coming up with what this definition of interesting is going to be really key, really, to understanding what it means to be a very successful auto reward generating agent. And I just think we need some sort of example of where an agent has been trained purely using auto rewards, but with this perhaps grander meta reward surrounding it. If we can just show that it produces something similar to where we're like, wow, how on earth did it do that without it ever, like we haven't even told it anything about that area of the challenge, and yet it's found that itself and learned how to do it. It's kind of like a step above what we're doing at the moment, which is just telling it, asking it, how do you solve this task? And it does it. It needs to want to solve the task.
Yeah, that's a really good way of putting it. Okay, well, look, we're getting on, and we might get cut off here because we do get cut off at 2. Now, for everybody who doesn't get the questions answered, please go to the Slack channel and everywhere else. Or just jump on and contact David and send him your CV. Okay, lastly, Miguel Martinez asked, what does the AGI community believe about consciousness? Which is, I guess, the final philosophical straw for you.
Yeah, there's loads of good material out there. I'd highly recommend like Max Tegmark's books. Life 3.0 is fantastic. That talks about consciousness. There's also even books around like why do we sleep. That's a fantastic book as well. It sort of talks about dreaming and what that might mean when it comes to learning. That certainly has a part to play. The AGI community is very diverse. It sort of ranges from the people who don't think it's possible at all through to those who think we just need to build bigger deep neural networks. So you can decide for yourselves where you put yourself. But I think we're missing something. I think that the trick is
Penrose.
Yeah, Penrose, all of his material, exactly. I think the answer is probably in the middle somewhere, but we're still missing a key ingredient.
Well, look, David, thank you so much. That was a fascinating talk, an hour well spent for me, and I'm sure everybody else. So thank you very, very much, and expect a flood of CVs to your inbox, I would imagine.
Oh, well, thank you very much.
Thanks, everybody. See you next time.
Bye, everyone. Thanks.